Hello students, I am Chintan Patel and welcome back to the video lecture series of the fundamentals of machine design. In this lecture, we are going to look at the shaft examples, some of the shaft example. Actually, we have seen some of the examples of based on the shaft concept in the previous lecture also. And today we are going to look at some more example based on the similar concept, as well as there will be a discussion based on the another concept that is the design of the shaft based on the rigidity. Example of the same will also be explained in the same video, and definitely it will be helpful for you for your exam, and that is why I would like to share some of the examples first based on the previous concept. Later on we will discuss another concept and we'll move on to another type of the examples. So first of all, as you can see, the data of the example number 1 for this particular video is already on your screen, and I will use some annotation over here so that I can point out some data to explain you guys. Okay. Some of the data which is given in this given data is 600 mm diameter of the pulley transmit the 16 kilowatt power at a speed of a 400 rpm. Now this line contains at least a minimum 3 data. Now here the diameter of the pulley is provided, which is 600 mm. So you can denote it as a you can give the nomenclature as a D, capital D. The power transmission over here is the 16 kilowatt. So 16 kilowatt is our power, which will be represented by the capital P. The speed is given as a 400 rpm. So if you can consider the speed or rotation per minute, rpm is the rotation per minute, is represented by n. Now we all know that whenever they provide you the power and the rpm, then you can easily find out the value of the torque or the twisting moment which is required to transmit this much amount of the power. So this is going to be our first step. But first, what else they have given, we need to comprehend that a pulley is mounted on a cantilever shaft. Now the shaft is of the nature or of the shape cantilever beam. Now we all know cantilever is one type of the beam which is having the support at one end, and the another end of the beam is free. So this is the type of the cantilever beam, and the shaft is going to carry the pulley in the way that the cantilever beam that is supported. So we are going to support the shaft at one end, and on the another end we are going to mount the pulley on the shaft. Okay, so this is how we are going to interpret this statement. Next, the weight of the pulley. The weight of the pulley is 1500 Newton. So indirectly they have given one force which is acting on the pulley or the point at which the pulley is mounted. This particular force will always act in the downward direction, as it is the weight of the pulley. Now is driven by a horizontal belt drive. Now this is very important, because if you skip this part, then you will not be able to solve the example correctly. Now they have mentioned that the belt drive is in the horizontal direction, and that is why you will have to consider the belts which are going in a horizontal direction instead of the vertical direction that we have seen in the previous lecture. Now the shaft is made of the plain carbon steel 40C8. Now 40C8 is the nomenclature of representation of the carbon steel, which contains the different types of the proportion, different amount of the proportion of the carbon and different other contents. But we are not concerned about the content over here. We need to calculate the strength of the shaft and the stresses of the shaft based on the strength. Now if you look carefully over here, then beside the nomenclature they also have provided the value of the SYT. Now what is SYT? S stands for the strength, Y for the yield, and T for the tension. So whenever they provide you SYT or SYC, they are trying to give you the value of the strength or the maximum value that the material can carry, maximum value of the stress that the material can carry, which is given as a 330 Newton per mm square. So 330 Newton per mm square is the maximum amount of the stress bearable by the material. and SUT that is the ultimate stress that is the 620 Newton per mm square. Now they have given it in the differentiate manner. So if you consider SYT, it is the yield point maximum value stress, and if you consider SUT, it is the ultimate point maximum value stress. Okay, so if the coefficient of friction between the belt and the pulley is 0.3, now coefficient of friction is always represented using the notation mu. So mu is given as a 0.3. The angle of lap is given as a theta, which is 180 degree. Determine the shaft diameter. So we need to calculate the diameter of the shaft. This is how we are going to design the shaft. Take the fatigue and shock factors. Take the fatigue and shock factors as a KB 2 and KT equals to 1.5. Now how are we going to accommodate these two factors in our equation? We will see that in the upcoming slides. First we need to calculate the stress which is acting in which can be bared by the material during the working condition. So for that we need to calculate the allowable shear stress, but for allowable shear stress they have already provided two values of the stress. First is the yield point stress and the second is the ultimate point stress. So that we are going to use the ASME method. ASME method will provide us the optimum amount of the shear stress that can be considered for the design of the shaft. So what is the ASME method? According to ASME method, what are we going to do over here is we are going to calculate the shear stress using two different equations. This one is the first one and this one is the second one. How can we use? So this is one type of a factor of safety, a factor which is required to ensure the safety of the material. Okay, 0.18 SUT is based on the ASME theory. If you look into ASME theory, they will give you the answer of the shear stress equals to 0.18 SUT. Now this comes from the ASME, this bracket comes from the ASME, and 0.75 is our factor for our safety. So if you put the value of SUT in this equation, that is 620, then you will get the answer of the shear stress as 83.7 Newton per mm square. Now another equation according to ASME is 0.75 into 0.3 SYT. Now if you put the value of SYT in this equation, that is 330, then you will be able to calculate the answer of the shear stress as a 74.25. Now we have the two values of the shear stress. Now ASME itself indicates that you have to consider the smaller value out of the two answers. So it is visible from these two values that the smaller value is the 74.25, which will be considered as our designing criteria. So now we will see another step, that is the torque on the shaft. As I already mentioned during the explanation of the given data, that they have already provided the value of the power as well as the RPM, that is N. So from those values you can easily calculate the answer of the twisting moment or the torque. So equation to calculate the same is P equals to 2 pi NT by 60. Now over here they have the basic equation is 2 pi NT by 60 only. They have used some of the precaution over here in order to convert the answer in terms of the watt and Newton per mm square, Newton into mm. Now what are those precautions I would like to tell you guys is this one. Now they have provided the answer of the power in terms of kilowatt. So in order to convert it in terms of the watt, they have divided the entire equation with the 1000. Another thing that this will give you the answer in terms of the Newton into meter, but in order to get the answer in terms of the mm, we have divided the entire equation again with the 1000. This 1000 is for the kilowatt to watt and this 1000 is for the meter to mm. So if you look at this equation, it is the same equation that we have discussed in our theoretical lecture. So if you put all this value, then you will get only one unknown, that is T, and if you make T as a subject and simplify the rest of the equation using calculator, then you will be able to calculate the answer of the T as a 3.819 into 10 raised to 5 Newton into mm. So the answer will automatically come in terms of the Newton into mm. It will not come in Newton into meter. if you have divided the equation with the 1000, and if you haven't divided the equation with the 1000, then you will have to convert it later on after getting the answer. So it's better to divide the equation with the 1000 in the initial step. Okay, so the next step is to calculate the force acting on the belt. So basically this is a belt drive, and each and every belt is facing the tension force inside it. So tension force will be acting on the belt, and which should be calculated using the relation between those two forces. Now whenever the belt drive comes, you have to use this relation in order to calculate the value of the forces or the tension forces in order to calculate the value of them. So the relation between these two forces or these two tensions is given as F1 by F2 equals to E raised to mu theta. Now we know that mu is nothing but the coefficient of friction and theta is nothing but the angle of left. Both the values are provided in the given data. If you put this value, then the right hand side of the equation is already known. Now now by the simplification you will get the right hand side equation as a 2.566, and we will now have a relation between the F1 and F2 in this equation. We will utilize this relation in the upcoming slide. So let's start with the figure that is that can be seen using the words that we have provided. So if you consider the shaft, then the shaft is loaded using the cantilever method. So if you consider it, then the shaft is supported over here. This is the support of the shaft using the bearing. Bearing will always work as a support. The other point is free, and on this point no support is provided, only load is provided using the pulley. So pulley is our load on the free end. So as you can see, pulley is mounted with the cantilever method. So this is our pulley, and if you look from the side view, then your side view would look like this. That this is our pulley and this is our shaft in the middle, and pulley is mounted with the horizontal belt drive, and that is why we have represented two forces, F1 and F2 tension forces, which are acting on the belt in the horizontal direction. Now we can calculate the value of two forces using this method. What is the method? That the torque that is transmitted by the shaft or the pulley, that is represented by the T. Now we have the value of the torque from the previous slide. Okay, so we have calculated the value of the torque. Now we need to put that particular torque in this equation. T equals to F1 minus F2 into D by 2. That is the basic equation of the torque. Now we all know that torque can be written as a R cross F. R is the radius and F is the force. So the force which is driving this amount of the torque is F1 minus F2. Now this is our force, and R is nothing but the D by 2. So this is the very basic equation of the torque. This should not be the question over here. So that is why if you put the value of the T from the previous slide, then you will have left hand side totally determined. On the right hand side, if you put the relation between the F1 and F2 in this equation, then your equation will be in terms of the F2 only. So here if you take F2 common and make it as a subject, then you can calculate the value of F2 that is unknown from this equation, that is 813.05 Newton. Now if you put this value in the previous relation of the F1 and F2, then you will be able to calculate the answer of the F1, and this is how we calculated the both tension forces that are acting in the belt drive mechanism. Now another steps to calculate the diameter of the shaft is the calculation of the bending moment on the shaft. So first of all, we will try to calculate the bending moment using this method. What are we going to do over here? Whenever the example of the cantilever beams comes up, you will have to just multiply the total load with the distance of the horizontal shaft. Now what is the distance provided with the horizontal support is L. L is the distance which is to be multiplied with the total force. But here the problem is the weight weight of the pulley, which is acting in a vertical direction, and the forces or due to the tension are acting in a horizontal direction. So the direction of both the forces are different, and that is why we have to calculate the moment of both the directions separately. So first of all, we are looking at the moment due to vertical force. So if you look at the right section, then moment due to vertical force is represented by mv. mv is nothing but the load weight of the pulley which is acting vertically downward into distance of the support, that is L. So if we both know both the values of the distance L and the weight from the given data. If you multiply it, then you will be able to calculate bending moment due to vertical load. Your answer will always be in a Newton into mm, because we know that the load is in a Newton and distance is in a mm. Now for the horizontal bending moment, now we know that two number of forces are going in a horizontal direction, F1 and F2. Both the forces are in a horizontal and in the same direction, and that is why we can simply add two forces, and this addition will give you the total answer of the force in a horizontal direction. Into L will give you the answer of the horizontal moment. Now horizontal moment will also be in a Newton into mm. The unit will be in a Newton into mm. Now you need to calculate the resultant of both the vertical and the horizontal moment. How can you calculate the resultant? The resultant will be represented by m. M is nothing but the under root of mv square plus mh square. This is similar to the resultant of the two different forces. Okay, the same way that we used to calculate the resultant is utilized over here in order to calculate the resultant of the bending moment. Okay, so using this equation you can calculate the resultant. M is calculated by inserting the values of mv and mh, and if you calculate those values, then you will be able to calculate the answer of m. Now we have the total bending moment which is required to be endured, or which is required to be sustained by the shaft. Another thing required is twisting moment. Twisting moment we have already calculated in the previous slide. So we have two criteria. First one is the twisting criteria and the second one is the bending moment criteria. Now both the criteria are to be satisfied in order to have a successful design of the shaft. Now if you consider the bending and twisting both together, then you will have to consider the case number 3, combined bending and twisting moment design. Now whenever you design this type of an example, then equivalent torque is to be required to be calculated, and for that TE is represented over here with this equation, and in the TE equation you can find out the value of KB and KT, which are the fatigue factors for the bending and twisting moment. Okay, so we know the value of KB and KT from the given data. We know the value of M and T from the calculation that we have carried out, and if you put all these value in this equation, then you will be able to calculate the answer of the TE, and your answer will also be in terms of the Newton into mm, because our bending moment and torque are in a Newton into mm. Now if you put the value of TE in the basic equation of the design of shaft, then our basic equation is nothing but this one, that tau max is equals to 16 into TE upon pi d cube. We have calculated the value of tau max, we have calculated the value of TE. Now the only unknown that remains in this equation is D. So if you put all these values in this equation, then and simplify the answer, then you will be able to calculate the answer in terms of the D, and the D comes out to be 46.07 mm. But we have converted into our standard data. Standard data is 48 mm. So how can we calculate the standard value? You can easily calculate the standard value by considering the standard forms of the theory. Okay, so this is how you are going to calculate the standard diameter of the shaft, that is nothing but the 48 mm. So this was the end of our example. Now we will move on to our new method to design the shaft. The new method is design of the shaft based on the torsional rigidity. Now torsional rigidity is a new term for you guys, but you have already studied the theory of the same in the chapter torsion Okay, so what is the theory of the same is given in this slide. As you can see, in the certain applications like the machine spindle, it is necessary to keep the angle of twist or the torsion deflection within the permissible limit. So if your shaft is twisting beyond the permissible limit, then it will also fail the shaft during the working condition. And as a designer, we do not want to fail the particular product which we have designed during the working condition. So that is why whenever an angle of twist is given in your example or modulus of rigidity is provided in your example, you will have to design the shaft diameter using this equation once. Once you calculate the diameter using this equation, once you calculate using the previous method, then you will have to select the diameter which is best suitable for the working condition. So how are we going to do the same in this particular method, that I will discuss in the upcoming slide. First of all, you will have to look at the equations that are mentioned in this particular slide, that the basic equation of the torsion is given, that is T by J equals to G theta upon L. If you make theta as a subject, then your rest of the equation would look like a TL upon JG, and TL upon JG can be converted in terms of the degrees by multiplying 180 by pi. So your answer will always be in a 180 by pi. Now another term which is given in your theoretical portion over here is the torsional rigidity or torsional stiffness of the shaft is given by the KT, and KT is this KT and the previous case KT both are different. Now this is the torsional rigidity, torsional stiffness. Okay, so T by theta equals to Gj upon L. This is the value of the torsional rigidity. Now I guess I have already covered this torsional stiffness or torsional rigidity term in the video of the torsion, chapter number torsion. So we are not going to waste much time into that. We are going to jump into our example number 2, which is solved using based on the mentioned method. So if you look at the data which is provided in your example over here, then you will be able to identify that determine the diameter below which the angle of twist of the shaft and not the maximum stress is controlling the factor in the design of the solid shaft. Now they have clearly mentioned that the factor which are controlling the design of the shaft are angle of twist and maximum stress. So the first factor is angle of twist, which I have told you that we will be able to design the shaft using the torsion equation. The second factor is the maximum stress, and the maximum stress factor is the factor which we have used in the first method of the shaft. So tau T equals to pi by 16 tau d cube is the equation using the first factor. Okay, so they have told you clearly that you have to design a shaft using both the factors. Okay, so first of all, the given data itself indicate that the allowable shear stress is 56 megapascal. So shear stress value is given, and the maximum allowable twist is 1/4 degree per meter. Now they have provided the value of degree per meter. What do you mean by degree per meter? They have already provided the value of theta by L. Theta by L or 1/4 value in a degree per meter means length is 1000 mm. Okay, you can also consider in that way, or you can also write in this way that I have mentioned over here. Now I will erase this so that you guys can understand the furthermore. Take G value. G, what is G? G is the modulus of rigidity. So if you summarize all the given data, then the given data would look like this. As I mentioned, the value of the shear stress is given, the value of theta is given, and the value of length is also given, because per meter means that they are mentioning 1 meter for the angle of twist. So 1 meter length equals to 1000 mm. The value of G is also provided. Now what we need to do is to calculate the diameter of the shaft using the first method that we have used in the previous examples. So what was the first method? First method is to calculate the diameter of the shaft using this equation. Tau max equals to 16 T by pi d cube. if you put the value of the tau max in this equation from the given data, it is 56. Now we will need a torque. They have not mentioned the value of the torque over here. So first of all, we are going to put this value as it is in this equation. Okay. So let it be over here in terms of the torque. We are going to find out the value of the torque in the, using the second equation, second method. What is the second method? Second method is based on the torsional rigidity. So equation of torsional rigidity is theta equals to TL upon Jg. So if you put the values of the TL upon Jg, whatever the given, first of all you need to convert the radians in terms of the degree by multiplying the answer with the 180 by pi. So this is the same what we have done over here. Now we know the value of the J, equation of the J for the solid circular shaft. Now what is the equation of the J? Pi by 32 d raised to 4. Now this is the equation of the J. The value of G is provided. The rest of the value are simplified a bit further. So this 32 goes over the in the numerator, and the rest of the values are like this. Now if you put the known values, so what are the known values? The first thing is this length is known as a 1000 mm. Now this G is provided as a 84 into 10 raised to 3. Now theta is also known as a 1 by 4. As we have converted it into the degree, now we do not have to convert it into the radian. Okay, so as it is, we have inserted it. Now the diameter itself is in terms of the torque. Now if you compare this equation and this equation, the first equation is in terms of the d cube. This is our first equation. This is the first equation, and the second equation is in terms of the d raised to 4. So this is our second equation, and if you take the ratio of both the equation, d raised to 4 divided by d cube, then your t, the t which is not given in your answer gets cancelled out from the ratio. This t and this t gets cancelled out, and you will get the answer in terms of the d, because d cube and d raised to 4 is going to cancel out in terms of the d. So your answer of the diameter will be in terms of the d, and that is 305.39 mm. So that is the diameter of the shaft. Whenever they provide you the value of the angle of twist, value of the maximum shear stress, then you will have to go for the both the equation that we have discussed in our entire theoretical portion. So with this, I will just end up this our session of the examples of shaft. We will see few more concepts and the examples in the upcoming lecture. Thank you.